Hi everyone, this is the next video in the sequence. This is exponential growth and decay. This is relating a differential equation to growth and decay models. You can see the objectives here, and so let's get started. Okay, so exponential growth and decay models start with a differential equation. All right, and so the differential equation has three basic parts. The part on the left just means that this is the rate of change of y with respect to time, or t. All right? This arrow actually points to the equal sign, and it is the word is. So the rate of change of y with respect to t is equal or is proportional directly proportional, if you remember this from algebra, directly proportional to y. All right, so if y is a differentiable function of t such that y is greater than 0 and y prime equals ky for some constant k, then y, this right here, y equals ce to the kt. This is an exponential function, growth or decay, all right, where c is the initial value of y, right, the beginning, c sub 0. K is the proportionality constant, constant of proportionality. In a linear equation, that would be the slope. And if this k value is positive, then this would be exponential growth. And if k is negative, you would have exponential decay, right? So graphically, for growth, we're talking about something like this. C would be the initial value, where t equals 0. And then decay, same graph, would look more like this, where the x-axis is an asymptote. Okay, so the red is decay, and the blue is growth. Okay, so the proof of this, what we're trying to end up with is y is equal to c e to the kt. That's what we're trying to get equal to. All right, so we're going to do like we do any proof. What I'm going to do is separate the variables. So I'm going to divide both sides by y, so that's going to give me dy over y. And that's going to be equal to k dt. All right, now I'm going to integrate, and that's going to give me the natural log, absolute value of y, equals kt plus c. Okay, and I put c sub 1, right? So I'm integrating with respect to t, and I'm verifying. Okay, so if I differentiated this here, I should get back to my differential equation, right? So that's the check. Then I want to solve for y, so I'm going to e both sides. And so this is going to give me y equals e, and remember from class when we had the problem where we have these two constants equal to or plus each other, I could split them up by multiplying them this way. Okay? So if I let the constant, since a constant is just a constant, and this right here is a constant, I'm going to set that equal to this number here. Okay, e to some power is just a constant. And then what I end up with is y equals c e to the kt. And so this proves that this is the general solution to that differential equation. So all solutions of dy dt equals ky are of the form y equals ce to the kt. Okay, so here's our first example. It says that the rate of change of y is proportional to y. So from that, we can say that y prime dy dt is equal to k y. All right, that's what that means. The rate of change of y is proportional to y. And it says when t equals 0, y is 2, and when t equals 2, y is 4. What is the value of y when t equals 3? All right, so if y prime equals ky, then y is equal to ce to the kt. All right? So the first thing that we need to do is we need to find c. We need to find the constant, and we're going to use the initial condition, right? So y is 2 to the k, and when t is 0. So we're using the initial condition because it doesn't matter what k is. You multiply it times 0, you get 0. Okay? So that would mean that this is 1, right? E to the 0 is 1. So c is equal to 2. All right, so now that you found c, we can now find k, the constant of proportionality. We can find k. So we're going to not use the same one, we're going to use this one here. So y is 4. The constant is 2. E, we don't know what k is, but we know that t is 2. All right, so I divide both sides by 2, and I get 2 equals e to the k 2k. I'm going to natural log both sides. So the natural log of 2 equals 2k. Let me erase that. The natural log of e, so this will just be 2k. 2k. And so k is going to be the natural log of 2 divided by 2. That's its exact form. If I were putting that in a calculator, natural log of 2 divided by 2, closing the parentheses, I should get 0.3466. And that is my constant of proportionality. That is k. That's what we found. Okay, so now that I have an equation, my equation is y equals, c is 2, e. I know what k is. K is the natural log of 2 over 2 times t. That's my equation. And it says, what is the value of y when t is 3? So this is just a calculator problem now. Y equals 2, e to the 3 halves natural log of 2, and so y is going to equal approximately 5.657, and that is your value of y. So the cool thing about differential equations is that they can be used to model phenomena in math and science and engineering and other applications can be readily modeled by these two models. And one of the models that can happen here is radioactive decay. And so the radioactive decay, the rate of decay is proportional to the amount present. T is time in years. It's measured in half-life, which is the number of years it takes for an atom to decay by half. So if you start with 10 grams, half-life would mean it would take the amount of time necessary to go from 10 to 5 grams, right, half. And so that can be modeled by R. Let me get my pointer. R is equal to CE to the KT. That looks familiar, does it not? That's the general equation of a differential equation. Okay, so the example is 10 grams of plutonium with a half-life of 24,100 years. How long will it take for 10 grams to decay to 1 gram? All right, so it's not a half-life, so it's going to be 10 and then down to 1. All right, so let's write our given, just like we had on the previous problem. We had t equals 0. At t equals 0, y is 10 grams. So I have 10 grams at the beginning. At some time, I don't know what it is, y will be 1 gram. Okay, it has a half-life of 24,100 years. So that would mean that when t is equal to 24,100 years, y will be what? Well, 10 divided by 2, right, half-life, or 5 grams. So this is the data that I need. And so I'm going to start off with my y equals CE to the KT, and I'm going to solve for C, right? So I'm going to start with my initial condition, 10 is equal to CE to the K times 0, so C is going to equal 10. That is the initial amount. And if you'll remember what we said before, C is the initial amount that you have. Okay, so then I need K. So I know that, I'm going to use this one right here, the half-life. I know that 5 is equal to 10 e to the K times time, which is 24,100 years. Okay, so this is going to be 1/2 equals e to that, 24,100 K. I'm going to natural log both sides and solve for K. And K is going to be the natural log of 1/2 divided by 24,100, and that's going to equal K. All right, so now what they want to know is what's the time. Wants to know what the time is. So I rewrite my formula, and I'm kind of running out of room here, but I have y equals 10 e to the this times t. All right, and so I know what y is, right? I'm using this. So 1 equals 10 e to the, right? So this is 1/10 e to that times t. So if I natural log both sides, same kind of deal, the natural log of e cancels, and so I'll be left with this. And guys, you know that this is the part that I'm leaving off because I just don't want to write it 100 times. All right, so the natural log of 1/10, right? So I'm going to take the natural log of 1/10, I'm going to divide it by this. Now, what I did on my calculator is I figured what this was, and it's an awful looking negative exponents like negative 2.8761298 e to the negative 5, right? So I just used the STO command, and I just stored it in A so that I had it. And then when I got ready to do this, I typed in natural log 1 divided by 10, hit enter, and then divided it by A. And I ended up getting T was approximately 80,059 years. So please try that on your calculator, and if you have trouble with it, bring it to class. Another application of differential equations is Newton's law of cooling. And Newton's law of cooling, you can see the differential equation right here. It's the rate of change in temperature of an object, which is proportional to, that's the constant proportionality is K, to the difference between the object's temperature and the temperature of the surrounding area, the room, just wherever. Newton's law of cooling is used to determine the initial and final temperature, the amount of time it takes to cool, the amount of time it takes a temperature change. In a body, in forensic science, they use Newton's law of cooling. So this is huge, and we're not going to finish this example in class. You're going to need to finish this as homework on your own, but I am going to get you started. So once again, you're going to do the same type of problem. You still need to find the constant. You're going to find the constant, a proportion, and then you're going to find the constant C, and then the constant of proportionality. So remember that the constant C is the initial temperature. Okay, so this looks a little bit different in that you've got a difference in temperature, but it's still the same procedure. So for instance, I'm going to start off with dy dt, the derivative of y with respect to t, is equal to k, and then y minus 60, because 60 is the constant temperature of the room. All right, and so if you separate the variables, I have dy over y minus 60 is k dt, right? And I'm going to use that to integrate and solve for c. So this is the natural log of y minus 60 equals kt plus c. I'm going to e both sides, and so y minus 60 is equal to e to the kt times e to the c, and I'm using c sub 1. Remember that this is just a constant, and so y equals 60 plus ce to the kt. All right? So once you've separated the variables, integrated, the next thing you have to do is solve for the constant. So solve for the constant, c, right, using the initial condition. And the initial condition is when t equals 0, what is the temperature? Well, the temperature, y, is 100 degrees. So I'm going back to this, and I'm solving for c. Once you have that, then you want to solve for k, the constant of proportionality. And then once you have solved for k, then you are going to go ahead and try to find the number of minutes, how much time it takes to decrease that to 80. So in other words, at t equals some time, y is 80. Okay? So that's the problem I want you to work on. And I will see you then in class. You can check your answer. Time will be less than 30 and more than 20 minutes, by the way. And I will see you then.